Hi, awesome chemistry students. Welcome to your last ever chemistry COVID-19 school closure video lecture. I'm sure this is such exciting news for you, and I am also thrilled that I get to stop teaching through my computer. I miss your faces, so I hope you're all doing well. Get strapped in. This is our last lecture, and it's going to be about ideal gases. We talked about last week behavior of gases and how we could quantify that behavior using certain variables. We talked about pressure, volume, temperature, and number of moles. So those are these four right here: pressure, volume, temperature, and number of moles. And all of the gases that we talked about last week are considered to be ideal gases. Now, I didn't really introduce this terminology to you then, but I'm going to today. An ideal gas is one that behaves like the gases we talked about last week. So when the particles collide, they just bounce right off. They have perfectly elastic collisions. So an elastic collision means that you don't lose any energy when you collide with something. So an ideal gas, consider two particles, they bounce off of each other and then they bounce back with the same thing. Now, elastic collisions don't exist in real life. Think of a bouncy ball. If you drop a bouncy ball, it'll bounce and it'll come off the floor, but it loses some of its energy, which is why over time, those bounces get smaller, 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 smaller. Or you can picture, you running into a wall. That's not an elastic collision. You immediately lost all of your energy and probably fell over if you've ever run into a wall. So ideal gases, we are pretending that no energy is lost when these particles collide. We also assume that these particles have no volume, that they're essentially so small that they don't take up any space, and these particles are not attracted to each other, meaning that they don't have any intermolecular forces connecting them. Now, we know that this is an ideal world. That's why we call these gases ideal, because that is not how gases act in real life. Now, in real life, these gases do experience intermolecular forces, and they do not have perfectly elastic collisions. They lose energy when they hit each other. But we also know that those gases have volume. I mean, it's a small volume, but gases do have volume. The thing is, for the most part, these gases, real gases, behave nearly ideally at room temperature and standard pressure. So that's why we're always talking about STP, standard temperature and pressure. We're always concerned about that ideal behavior of gases. But when we start to get higher temperature or lower temperature or higher pressure or lower pressure, we tend to lose that ideal gas behavior, and we get back into this stuff up here that says we will lose some energy after those particles collide, and they do take up space. So we have to consider more complex mathematics if we treat gases as real gases. But we are only going to talk about ideal gas behavior because the math is simply too complicated for us to assume any real gas behavior. So we are going to talk about everything that we talked about last week with pressure, volume, temperature, and number of moles. Today, now that we've sort of introduced this ideal gas behavior, we are going to learn one equation, one perfect equation. It's like the one ring. This is the one equation to rule them all. This is the ideal gas law, the law that combines all four of these variables. It tells us how gases behave. So here is that ideal gas law. It's PV equals nRT. Now, this is without a doubt one of the most memorable, important equations that you will ever learn in science. I'm sure that if you ask your parents about their chemistry classes or said something about the ideal gas law, my guess is that they would remember this equation. That's just how important of an equation it is. And in this equation, we are already familiar with all of the variables. So P, pressure, V, volume, N, number of moles, T, temperature. The only new one is R. R is an ideal gas law constant. So this is just a constant value that we plug into an equation to make sure that this equality stays the same. It's basically there to adjust for any ideal gas behavior. So it's there, but we don't have to worry about it. It's a constant. We just plug it into the equation. And there are two values. One value is 0.0821. One is 8.314. But what is different? Obviously, these have such drastically different numbers, 0.08, that's almost zero, versus a number in the eights. How is it possible that those can both be the same number? Well, you have to look at the units. I've been telling you guys all year that units are so important. These two numbers are exactly the same. They just have one small difference. They're units. If you look, we have all of the units from all of these variables, ATM, kPa, those are pressure units. Then we have liters, so kPa or atmosphere times liters, so that's our volume component, divided by moles, which is the unit for N, and K, the unit for temperature. So we have this whole unit that's one giant monster unit of all four of those variables that we talked about last week. But the thing is, we have the potential for two different pressure units. So you can use either of these values for the ideal gas law constant or R. You just have to pay close attention that your pressure units match the units of the R that you choose. So let's do an example. It says if I have 3.5 moles of a gas at a pressure of 895 kPa and it takes up a volume of 50 liters, what is the temperature? So just like all those previous problems that we did last week, the first thing that we're going to do is sort out the question. What information do we have? Unlike the equations and the gas laws that we learned last week, we don't have a before and after. The ideal gas law is awesome because it can tell you in a snap the exact, what any sort of information that you need to know. You don't have to have a before and an after. You don't have to make a change. It can tell you the instantaneous value of one of these variables. When you see 3.5 moles, you don't have to designate it as N1 or N2. You just say this is N, okay? And then it says we have a pressure of 895 kPa, so we have P, and it takes up a volume of 50 liters. So this is volume. And it says what is that is what we are going to find. Now, I've already told you that we are going to be using the ideal gas law, PV equals nRT. So let's just make sure that we have everything accounted for here. We do have pressure, we have volume, we have N. R is a constant, so we just have to scroll up to find it, and we are going to find T. So looks good. What we do want to determine is what value of R we are going to use. Remember, there are two values for R. One has atmospheres for its pressure unit, one has kPa for its pressure units. Since our pressure is in kPa, we need to use the second value of R. So R equals 8.314 kPa times liters over moles times Kelvin. This is a very complicated unit, but you'll see it all works out. So we should now have everything that we need to solve for T. But just like last week, what I want you to do is get T by itself. So isolate this variable here. So we are going to need to divide both sides by N times R. When we divide both sides by R, we get T equals PV over NR. So now we've solved for our variable. We just need to plug in all of our numbers. And this is the easy part. The pressure is 895 kPa. We're multiplying that by the volume, 50 decimal point liters. Remember, that decimal point is important. It tells us about sig figs. And we are going to divide by the number of moles, 3.5. and then multiply by R, 8.314 kPa times liters over moles times Kelvin. So let's just double check that all of our units will cancel. Because if your units don't cancel and we don't end up in Kelvin, then we made a mistake somewhere. We know that since we are solving for temperature, we have to end up in Kelvin. So this R value is where things get complicated because we have a fraction in the denominator. So we have to go back to our math rules. The numerator of the denominator will cross off with the numerator of the numerator. So we just lost our kPa and our liters because those are both in the numerator, sort of. Then, just looking at the bottom, the moles will cancel out with the moles because here the moles is in the numerator of the denominator and the moles is in the denominator of the denominator. So those will cancel out, and what we'll be left with is K, which is in the denominator of the denominator, which if we remember, so we have something 1 over 1 over 1 over K. And if we use our reciprocal math rules, ultimately this K becomes the numerator because we would have to multiply by the reciprocal and it's a whole thing. You end up with K. Now we just need to solve. Where's my calculator? Okay, we multiply the top, 895 times 50, and then divide by what's on the bottom, 3.5 times 8.314. And you get for the temperature 1537.85 Kelvin. But sig figs. We need to have 2 sig figs because of the moles and because of the volume, both telling us that we need 2 sig figs. So we need to keep just the 1 and the 5, which means it's going to be 1500 Kelvin. Those zeros have to be there for placeholders. And that's your answer. We just used the ideal gas law equation. Let's do another example. This one says, at what pressure in atmospheres does 16.3 grams of nitrogen gas have at a temperature of 300 Kelvin in a 25.0 liter tank? Okay, we got a lot of information. Let's break it down. So at what pressure? So it sounds like we're going to solve for pressure. So that's a question mark. And we have grams. Let's come back to that. We have a temperature and it's already in Kelvin. How convenient. And we have a volume. Okay, so if the equation is PV equals nRT, we know that we're going to solve for pressure. We know the volume. We know R. We know T. N. N is moles. Well, we know how to get from grams to moles, right? We could do that and then take that number and plug in the number of moles in for N. So that's probably what we're going to have to do there, and then we're going to be able to solve for pressure. It'll be all good. The value of R that we are going to use needs to match our pressure units. So the problem says in atmospheres. So we have to use the R value for atmospheres, which is 0.0821 atmospheres times liters over moles times Kelvin. And let's go ahead and do some math here. Let's start with converting the 16.3 grams since we know we're going to have to plug that into our equation. We've got 16.3 grams of nitrogen gas. Remember that nitrogen is diatomic. So we're incorporating a little bit of stoichiometry / unit conversions into this problem. We want to get to moles of N2. So our units are going to be grams on the bottom and moles on the top. Anytime you see moles and grams, you know you have to have molar mass. So molar mass of one nitrogen atom is 14.01, but we have 2 nitrogen atoms, so the molar mass is 28.02 grams. Then when we solve this, we get 0.582 moles of N2. So now we have our N value. Let's go back to this equation, PV equals nRT. We need to solve for pressure. So we need to divide both sides by volume. Those will cancel out. We'll be left with pressure equals nRT all over volume. Then we just need to plug in. We know the N value. We just calculated it, 0.582 moles of N2 times R, 0.0821 atmospheres times liters over moles times Kelvin, and then multiply that by the temperature, which is 300 Kelvin, and divide the whole thing by the volume, 25.0 liters. Again, let's take a quick look at our units. Moles will cancel out because in this complex unit, the moles are in the bottom and here they're in the top. The Kelvin will cancel out for the same reason. And then the liters, that's in the numerator of the numerator, so it will cancel out with anything in the denominator there. And we should be left with atmospheres. And then we just need to calculate it. So we multiply across the top and then divide by what's in the bottom. And our answer is 0.573 atmospheres, but we need to take a look at sig figs. With our sig figs, our limiting factor here is going to be that temperature. 300 only has one sig fig, so I'm going to need to round this to 0.6 atmospheres, and that is my final answer. That's pretty much the ideal gas law. It's just another equation. We're plugging things into it. The couple of tricks that you need to be aware of are the R values. And then if you get grams or something with a chemical equation, you know that you can get to moles because you guys are rock stars at doing that now. So this was sort of just a quick video. I recommend that you watch it again, watch those example problems again if you need to go back through them. And then it's just, I think, 6 questions on a worksheet, and that's it. Make sure that you get all of your work in by Friday at noon. And then have a great summer. Miss you guys. I hope you come see me in August. Okay, bye. I'm sad. Okay, but now I'm actually going, I promise. Bye, guys.